here is section 9.10. Obviously the last section in this chapter, and actually this is even the last lesson that I have to record, so I'm pretty darn excited. I did chapters 10 and 11 first to be done with them, and not knowing how long I'd be here either, I guess, but last one. So our objective today is what we're going to do is take our Taylor and Maclaurin polynomials that we wrote back in section 7, I believe it was, and now we're going to write those as a series. So if we form a convergent power series, basically this is what our polynomials look like. Oh, got an announcement here. They have, we know that from our Taylor and Maclaurin series, their polynomials, sorry, they look like this. And what we want to do is just to be able to write this as a power series. So to write this as a power series, we have the summation. I would definitely start at 0 for our first term, and we go to infinity. And then we can take, we know here in our denominator, that would just be n factorial. And actually in this situation it's really nice because it's the nth term is written, not that it would be hard to find. But we need to take the nth derivative of our function. We're still plugging in c wherever we're centered around, and then we have x minus c to the power of n. So taking our Taylor and Maclaurin polynomials and writing those as a power series. Well, if we look back, we want to compare examples here for number 3. Looking at our example, if we have just our function f of x equals e to the power of x if we're centered at 0, and then compare, well, what happens if we want e to the power of 3x? So if we just slightly change it, what does that do with our polynomial or with our series? And then the last one down here, c, is, well, what if we want to have e to the power of x cubed? And so just looking at how we can change things if we start from a really basic, or like the most basic form. So if we look at e to the x, maybe some of you remember what that polynomial is equal to. It's also really easy to create this one. I always start with my function, so the function we know is e to the x. I need the first derivative. Well, this is awesome because the first derivative is e to the x. The second derivative is still e to the x. The third derivative is still e to the x. Remember, we plug in what we're centered around. So if I plug that in, if I'm centered at 0, e to the power of 0 is 1. Maybe I shouldn't write an equal sign. Maybe an arrow would be better there. Plug in a 0. E to the power of 0 is 1. E to the power of 0 is 1. So this is nice. I'm just, in all of these, obviously the coefficient is equivalent to 1. When we write our polynomial then, so we're writing this function, we're approximating it with a polynomial. Our first term comes from our original function, or from that first term here, it would just be a 1. We add to it, it would be 1, which I'm not going to write in there, times our x minus our centering point. Well, x minus 0 would just be x. Technically that's to the power of 1 divided by 1 factorial. And I know those don't have to be written in, but sometimes it's nice to do that just to see the pattern on what's happening. So then when I go to my next term, which deals with my second derivative, again the coefficient is a 1. Well, I'm not going to write that in. Then I have, it would be x minus my centering, which is 0, so it's just x. That's squared divided by 2 factorial. And I think some of you probably remember this polynomial. It's a pretty nice one. And we know that these terms would just continue. Well, if I want to write this now specifically as a power series, we have to write this thing as a power series. So this polynomial is going to be equivalent to the summation. We're going to start at 0 again, so n equals 0. We go to infinity, and it would be x to the power of n divided by n factorial, which is pretty basic when you look at it, because obviously here, well, I don't have anything, so anything to the power of 0 is going to give me 1. 0 factorial is 1. You know, plug in a 1, plug in a 2, plug in a 3. That's a pretty easy one to get. So what this section, what we want to do is start with a really basic function. Like e to the x is as basic as it can get. And then, like for letter B here, well, what happens if I change it and I want e to the 3x? So we're slightly going to change. And you could go through and do this and say, well, okay, I know my original function is e to the 3x. Then when you take your first derivative, so we're going to write our polynomial just like we did with the last problem. And when we take this derivative, we have e to the 3x, chain rule, the derivative of the exponent would give us times 3. The second derivative, we don't need to use the product rule because it's a constant, and then here would be our variable with that. So it's still going to be e to the 3x. But the derivative now of 3x is 3, so 3 times 3 would give us 9. Our third derivative, we know we're going to have e to the 3x. And then what's the derivative of 3x? It's 3, so 9 times 3 will give us 27. And we could continue this. 3 terms or 4 terms here should be sufficient. Again, plug in a 0 to get our constant. So if I plug in a 0, I'm going to get 1 for an answer. If I plug a 0 in for this problem, I'm going to get 3 for an answer. If I plug a 0 into this problem or function, I get 9. If I plug it into this function, we get 27. So looking at this, obviously here if you forget to use your chain rule, you're in big trouble because your constants are going to be wrong. But now I can write my polynomial, and it's 1 plus, now because that's taking our first term, the next term with the first derivative, I have that 3 centered at 0, so I'm not going to write in there x minus 0, but it's x to the power of 1 divided by 1 factorial. And I know that you can simplify this, but again, like I said, it's really nice to write it all out because then you can see the pattern on what's happening. So the second derivative, okay, I know that the constant is a 9, so it's 9x squared divided by 2 factorial. And the third term would be 27 x cubed divided by 3 factorial plus ... as we go through here. Well, now if I want to write this as a power series, my power series doesn't really change that much from the first one that I did that we had up here in A. So there's not too much change from this. I still have, like, the denominator is definitely still going to be n factorial. And in the numerator, we still have x to the power of 1, x squared, x cubed. And then how do we go from 3 to 9 to 27? Well, if we look back, we know that we kept multiplying by 3. So this we could write it as 3 to the nth times x to the nth. Well, in this situation, so this is good, and it's obviously what this would equal. But what we can end up doing with this thing is because your exponents are the same, you can write it as 3x to the power of n. That's divided by n factorial, and then obviously it went from 0 to infinity. What I want you to get out of this is if we look at A, and if we, okay, our original function is just e to the x. Very simple to create a power series for that. It's very easy to create a polynomial for it too if you forget, and then but this is a power series that you might memorize because you're going to use it so often. Well, now if I just change and I say, well, instead of x, I want it to be to the power of 3x, all that you really have to do is in place of x, I want that to be 3x. And that's really nice. It's really powerful, and it'll allow us to write many power series very, very quickly without having to show all the work for it. So now if we go down to letter C and say, well, I want e to the power of x cubed, well, now in place of x, I want it to be x cubed. So I can use the same power series. I'm starting at 0. We go to infinity. And in place of x, I want it to be x cubed, and that's to the power of n. Still divided by n factorial. So if you look back, it's okay, in place of x, because here I had an x. Well, there is my x. In place of x, now for C, it became x cubed. There it becomes x cubed. And from here, it's probably would be nice, power to a power, we multiply those together. I guess you don't have to put them together. You could say it's just x to the 3n. But this is a nice thing because if we tried to do this and take the derivative with it, it gets ugly really fast. So if we did it the way that we did in the previous two problems, our first derivative is easy to do. You have e to the power of x cubed. Derivative of the exponent, sorry, is 3x squared. But now once you start taking this derivative for a second derivative, you have to use the product rule. So that would mean we have derivative of our first term, 6x times e to the x cubed, plus, keep the 3x squared. Derivative of this term would give you another times 3x squared, e to the x cubed. Well, now to get to my third derivative, I'm going to have to use the product rule here, and I'd have to use the product here. And you could definitely put those two terms together, but you still have e to the x cubed. So this is a situation where you start with your derivatives, and they just, I'd consider them to blowing up really fast. They get huge. And you're going to use the product rule many, many times, and that's annoying, and we don't want to do that. So what we want to do is start with a very basic, simple series. And then if I say, well, what happens instead of e to the x, what if I want e to the x squared? Great. All we have to do is replace x with x squared. Just like if I want e to the power of 5x. Great. Replace your x with a 5x. So it's a property of series that we can do. You just have to start with a very easy easy function to start with and make that series for it. Alright, so if we move on and we have another type of example, same kind of progression that I just did in the last one. So we have a power series. If we look at the a and b, we have sine x, and then we're going to look at, well, what if I want to take my sine x and I square it? These have to stay centered at the same thing. If I say, well, this one is centered at 0 and this one is centered at 1, then I can't do that. They have to be centered at the same thing. But in this situation, okay, this is good. This is what what we want to deal with. So sine x is something that we're going to actually end up using quite a bit. And you'll probably end up memorizing this one, this power series for it. Our function, again, it starts at, it's just sine. Move on, our first derivative is going to be cosine. Plug in, or we want the second derivative, which is negative sine. Third derivative becomes a negative cosine. Fourth derivative, we go back now to sine. And we know that now, because sine and cosine, we're just going to keep going through the cycle of this. We need our coefficient. If you plug in a 0, sine 0 is 0. Cosine 0 is 1. Sine 0 is 0. Cosine 0 is 1. It's negative, so that's a negative 1. Sine 0 is 0. And now I hope that you understand we just keep going back through this pattern. Now, write your polynomial. And maybe you want to even pause this and you write out what the polynomial should be. So if you have this situation, pause it and write your polynomial. Know that here you will be alternating. So you're going to go from positive to negative, and write out just the polynomial right now. You don't do the power series quite yet. Okay, so if you write out your polynomial for this, your first term is 0, so it's 0. Here, or I shouldn't say term, but that first part of that is 0. So here's a 1. That's with my first derivative, so that would be x to the power of 1 factorial. This, if I have a coefficient of a 0, it's going to wipe out that term. Here I have a coefficient of a negative 1, so I know I'm alternating. It goes with the third derivative, so it's to the power of 3 divided by 3 factorial, etc. Here's kind of my way how to remember this, is I know that sine is an odd function. Because you're going to want to know the difference between sine and cosine, so that you can easily go through and write out what your polynomial is. Sine is an odd function, so it's the odd exponents that you're going to deal with. It starts positive and then obviously alternates from there. So when we write this now as a power series, we have our summation. You can start at 0 or 1. It doesn't matter. It really doesn't matter for this. I usually start at 0, but if you started at 1, that's completely fine. The series would be a little bit different, but it's okay. Let's start with the denominator. So if I go from 1 to 3 to 5 to 7, I know the next one will be 9. This is an arithmetic series. You're changing by 2 every time. So it's going to be 2n because you're changing by 2. If I plug in a 0, my first number has to be a 1. So I better add 1 to this and then make it factorial. So if I plug in a 0, my first term, yes, it'll give me 1. If I plug in a 1, representing this one, well, 2 times 1 is 2, plus 1 is 3. There's my 3 factorial. If I plug in a 2, definitely going to give me 5. If I plug in a 3, definitely give me 7, so I'm good to go. You have to deal with the alternating part and deal with it completely separate. So I know I have a negative 1. I want my first term to be positive. So I have to have it either to the power of n or to the power of n plus 1. Well, if anything to the power of 0 is always going to give you a positive 1. So great, that's going to work for this one. And you can check, well, you know, like here's if I plug in a 0, a 1, a 2, a 3. If I plug in a 1, negative 1 to the power of 1, yeah, it's negative. This is negative. If I plug in a 2, negative 1 squared is going to be positive. Yep, that's positive. So there we've dealt with our alternating portion. And now we have our exponent part with this. Well, these things, if the exponent and the denominator are obviously the same thing. So that's just x to the power of 2n plus 1. So it's obviously it's a little bit more than just e to the x. E to the x was so easy to create a power series for. But sine you're going to have to use quite a bit. So this is one that at least be able to write your polynomial out quickly. And then make sure that you're used to this. Like, okay, this shouldn't look weird to you after you do this section because we're going to see it quite frequently. Well, what's nice that we have already have this one established. So when I come down to letter B and I have its sine x squared, this is not sine squared, it is just my x value squared. We can do what we did in the last, like in the last examples. So if I'm just changing the x, then I can go through and back at my, go back to like the original, the most basic power series, and you can change just the x. So that allows us to write this power series very conveniently. It's a summation from 0 to infinity. We would have negative 1 to the power of n, and in place of x, which I had sine x, now I have sine x squared. I have x squared. This is to the power of 2n plus 1. This is all divided by 2n plus 1 factorial. And you can leave it like this. We've created our power series. We're good to go. In this next example, though, I am not changing the x. I'm changing this one so that it's sine squared. This is a completely different scenario having sine squared. If you can only do what we were doing with the replacing when you're only replacing the x. So in this situation, we know that our original function f of x, this means it is sine of x. We want to square that entire thing. You could go through and try to write your polynomial out with this and say, well, what is my first derivative, my second derivative, etc. That one is going to get big pretty fast. So I'm going to give you a hint. In this type of a problem, specifically if you have just sine squared or just cosine squared, we want to use power reducing. So if you remember back to chapter 8, which now is a really long time ago for you because it was like in February and this is April, you have sine squared of x is equal to power reducing. Remember it's 1, it's minus cosine, double your angle, so that makes it 2x divided by 2. And we'll just write in here what cosine squared is in case you have to use that. And it's the exact same thing, but you're adding. It's cosine, double your angle, so it just makes it 2x divided by 2. So we want to do this because now I'm just changing my x. Although it becomes cosine, but that's okay. But now I'm just changing the x value. I'm not changing the entire function. And I'm going to rewrite this thing as 1/2 minus 1/2 cosine 2x. So I want this idea. If I can write a power series for cosine x, I can really easily write a power series for cosine 2x. So I know that this started off as sine squared. We're going to end up using a power series for cosine in order to write what sine squared is. So sine squared and cosine squared, a unique situation. We want to rewrite using our power reducing, and now it allows us to just have a trig function and we're just changing the x value and nothing else. But if I'm rewriting and I have to write a power series for this, I better come up with a power series for cosine x. If I have a power series for cosine x, I very easily get a power series for cosine 2x. So you have plenty of room up here. Figure out what cosine x is going to be as a power series. So my original function, I might even want to go a little bit higher up here. If we have f of x equals cosine x, then f prime of x is going to equal negative sine x. Second derivative will equal negative cosine x. Third derivative is equal to a positive sine x. Fourth derivative is equal to cosine x. And we can keep going, but I hope that you recognize the pattern for this. We're still centered at 0, so we still take that into account. Cosine 0 is 1. We know sine 0, 0. Cosine 0 is 1. That makes it a negative 1. Sine 0 is 0. Cosine 0, 1. We should see our pattern. As a polynomial, this is 1 for that portion minus, I don't have to, if my coefficient is 0, don't even include that term because it's 0 times whatever. It's going to cancel that out. So then I'd have a negative 1. So it's minus, this is x squared divided by 2 factorial. Going down, it's a positive 1, so it's 1. That's x to the 4th divided by 4 factorial. And I hope from here we can see our pattern. Obviously now, I hope it's obvious, minus x to the 6th divided by 6 factorial plus x to the 8th divided by 8 factorial be minus dot dot dot. And our power series, we start at 0, we go to infinity. Remember, this is our power series for cosine x. That's what we started with, centered at 0. And here in the denominator, you have your 2, 4, 6, 8. Your first term would be a 0 factorial. So this is actually pretty nice, because this just ends up being 2n factorial. In the numerator, you have to account for your alternating, so I'm going to start off with a 1. Then is it to the power of n, or I'm sorry, start off with a negative 1. Whoa. Is it to the power of n or to the power of n plus 1? Well, I want my first term to be positive. If I plug in a 0, is my first term positive? Yeah. If I plug in a 1, is my next term going to be negative? Yeah. Then we have x, just like in sine, our exponent is the same as the denominator. So that would be 2n. So here's our power series for cosine. You will honestly want to know the difference between sine and cosine and make it at least start with your polynomial. I guess I can't say I have the power series memorized, but I do have the polynomial memorized. And for our polynomials, I know cosine is an even function. This technically is x to the power of 0 divided by 0 factorial, so that makes it even. But obviously, cosine is an even function, and it's alternating. Where I know sine, well, is an odd function. They both start off positive. They're both going to be alternating, but sine deals with the odd, and cosine deals with the even. And if you look back at, here, obviously they're alternating as you go through it. And that's why it's going to be one of them has odd functions, or one of them is odd numbers, one of them is even, but we know that cosine deals with our even, and sine deals with the odd. Alright, so now what we can do, remember we're back to solving this original problem here, what is sine squared equal to? And this is what I'm trying to solve for. It kind of gets lost in here, I guess. Well, we know sine squared is 1 minus cosine 2x divided by 2. And like I said before, we like that now we're only changing our angle and not changing our trig function. So we can write this way. Well, now you keep the 1/2 outside. And it seems a little bit weird, but just doesn't get included with our power function. You also keep this 1/2, so the minus 1/2 has a coefficient. And then you have your power series from 0 to infinity. You have your negative 1 to the power of n, and in place of x, we can replace it with a 2x. So it's 2x to the power of 2n divided by 2n factorial. So that's a pretty tough problem, obviously, compared to the last ones. But now that you know your power, or at least the polynomials for sine and cosine, you should be able to do this fairly quickly. It shouldn't take as much time from here on out. And remember that if it's sine squared or cosine squared, you do end up using power reducing. Because we just want to change the angle, we don't, the trig function changing that is a completely different story here. Well, if we look at another situation, now we have x times sine x, which again, pretty ugly, because you're not just changing your x. I'm multiplying this entire thing by another x. This is actually a pretty easy scenario though, because we know it's x, that's coming from here. We can write sine x very quickly as a polynomial. Sine is an odd function, so it's x to the power of 1 divided by 1 factorial. We know they have to alternate, so it's minus x cubed divided by 3 factorial plus x to the 5th divided by 5 factorial minus, I don't know how many you want to write in here, x to the 7th divided by 7 factorial plus dot dot dot. Well, if you're going to multiply this by x, we just have to distribute the x to all of our terms. Well, that's a really easy thing to do. So then I can just say, well, it's x squared divided by 1 factorial minus x to the 4th divided by 3 factorial plus x to the 6th divided by 5 factorial minus x to the 8th divided by 7 factorial again plus dot dot dot. But we had that original polynomial that we knew with sine x. To multiply it by x is not going to be hard. Now that I write this out, we can find the pattern and very easily write this as a power series. And I almost always start at 0. Again, if you wanted to start at 1, you definitely could. It's going to change it slightly, but that's okay. You can definitely do it that way too. So I'm going to start with the denominator. I don't know why I like to start with the denominator, but 1, 3, 5, 7. Obviously it's going to be an arithmetic here, so I'm changing by 2 every time, so it's 2n. My first term has to be a 1, so I better add 1. And that basically comes from our what it was to begin with for sine. Then I always deal with the alternating, so I know it's a negative 1, either to the power of n or to the power of n plus 1. Well, I want my first term to be positive, so if I plug in a 0, it's positive. When I plug in a 1 for my next term, great, it's negative, so that's good. Then I just have x, and I need to have the 2, 4, 6, 8. And in this situation, okay, again it's arithmetic, I'm changing by 2 every time, so it's 2n. But my first number has to be a 2, so if I plug in a 0, I better add 2 to get to a 2. So, in these situations, a lot of different ways, I guess, that I've showed you so far on how to write a power series for these. If you're only changing your x value, I hope that you understand that you can take that original very easy power series and just change your x. But if you're changing other than just your x, like we did in the last 2 examples, sine squared is pretty unique because you have to completely rewrite that. And now we can, we even went to cosine then. But now, okay, I have just changing my x and I can replace that. Here's a situation, oops, the next one here where, okay, I'm not just changing the x, I'm multiplying this entire thing by x. Well, write out the polynomial. If you know sine x and you're multiplying by x, it's really easy to write the polynomial for this. You don't want to have to start writing the polynomial the long way, saying, alright, if I have f of x and that's x times sine x, what is my first derivative going to be? Oops. So my first derivative, you use your product rule, and again, as soon as you start using your product rule, it's just going to get bigger and bigger and bigger usually as you go through this. So keep the things that you know. You should know how to write e to the x as a polynomial. You should know how to write sine x as a polynomial, and you should know how to write cosine of x as a polynomial very quickly, because once you know the polynomial, it's not hard to create the power series. Okay. Here's where it gets not different. It is different, but it's not necessarily even what I would call hard. Just a little bit weird for some of this. We want to find the first 4 non-zero terms of this Maclaurin series. Again, Maclaurin and Taylor, I never remember what the heck which one is, but it doesn't tell me where it's centered, so if I know that Maclaurin, that means it's centered at 0. Well, this is a disaster to start. We have e to the x times arctangent of x. And I can start and get my first term pretty easily. I guess if I went through and said, well, here's my f of x. That's e to the x times arctangent x. Then when I take my derivative of this, the derivative of the first term is e to the x times the second term, arctangent x, plus keep the first term, e to the x, times the derivative of arctangent, which is going to be u prime, which that's to be 1, divided by 1 plus x squared. Well, that's only my first derivative. If I do the second derivative in this way, I have to use my product rule again, and over here I have to use the quotient rule. So basically, we don't want to use this original. It's ugly. What we want to do is, if you have to find your first 4 non-zero terms, is multiply your 2 polynomials together. Well, I know what e to the x is equal to. E to the x is equal to 1 plus, it's x to the power of 1 divided by 1 factorial, plus x squared divided by 2 factorial, plus x cubed divided by 3 factorial, plus x to the 4th divided by 4 factorial, and there's e to the x. Arctangent x, we don't know that one yet. We better create this polynomial. That's going to be fun. Always look for patterns. The only way really to create a polynomial for this is to start doing the long way. Our function is arctangent x. Great. The first derivative, remember it's u prime, divided by, 1 plus u squared. The second derivative for this one, if we use our quotient rule, do we want to do that? Let's actually rewrite this as 1 plus x squared to the negative 1 and just use the chain rule. So that will give us a negative 1 times the 1 plus x squared to the negative 2. So it's 1 plus x squared squared. Chain rule, the derivative of the inside is 2x. No, 2x. Ugh. If we look at, we better take at least one more here. I'm going to rewrite this as negative 2x times 1 plus x squared to the negative 2. Now when I take the derivative, product rule, the derivative of the first term is negative 2 times our 1 plus x squared to the negative 2. Add to it, keep our first term. Okay, well, I guess that becomes a negative 2x. The derivative of this thing, oh boy, I'm going to multiply it by a negative 2, so it'll become positive. That'll become a 4. 1 plus x squared to the negative 3. Chain rule, the derivative of the inside is times another 2x, which would, I guess we could put that together and make it 8x squared. Here's the deal. Just memorize the one for arctangent. It's a heck of a lot easier. And we will here in a second. We're centered at 0. Arctangent of 0, if you plug in a 0, you get 0. That's not good because we want terms here. Centered at 0, if we plug a 0 into this situation, we get a 1. That's a really good thing. If we plug a 0 into our second derivative, unfortunately we get a 0. Ugh, that's not a good thing. If we plug a 0 into this third derivative, well, I know this term is definitely gone. in this situation here, I'm going to get a -2. Kind of ugly. You can write more terms. What I'm going to suggest is you just to memorize this polynomial, and it's a pretty easy one because tangent is also an odd function just like sine. It's not the exact same polynomial because obviously sine and arctangent aren't the same thing, but it's pretty darn close to being really similar. So if I look at my first derivative, that's the first time I have a coefficient, so it's just my first term is just x. It's technically to the power of 1 divided by 1 factorial. This term, it's a 0, so that's not going to affect it. Here I have a -2, that's x cubed divided by 3 factorial. And really the pattern that we can get from this is if we wrote this out, I know I have plus ... arctangent, and again it's just easier to memorize this one. Here that would just be an x. This, if I rewrite this, 3 factorial is 6, so 2 6 is a third, which will just give you 3. Then I'm going to add, the next term is x to the 5th divided by 5 factorial. Whoa, just kidding, it's just 5. Yikes. Then the next term would be minus x to the 7th divided by just 7. So it is incredibly similar to sine. The only thing that's different, obviously, with arctangent is that it's no longer factorial. It's just 1 in the denominator, 3, 5, 7. And that is, tangent is an odd function. Okay, so we've done a whole heck of a lot of work here and not even close to solving what the problem is. We only want the first 4 non-zero terms of this Maclaurin series. It does not say to write out a power series. You want your first 4 non-zero terms. So what we're going to do is basically take this polynomial for e to the x times this polynomial, arctangent x, and we have to figure out what our first 4 non-zero terms would be. So if I multiply these two things together, I'm kind of running out of room here. So I have 1 plus x squared over 2 plus x cubed over 6 plus x to the 4th over 24. Technically that can go on, so I have to use the ... And I'm multiplying it by arctangent, which is x minus x cubed divided by 3 plus x to the 5th divided by 5 minus x to the 7th divided by 7 plus technically ... that can go on. I'm not going to need more terms than this though because I know that I'm going to find my smallest. I need the first 4. So as I multiply things together, I'm going to take this 1 and I'm going to distribute. So I'm going to distribute it to a couple terms. I don't know how many I'm going to need, so I'll write out a couple of them. But if I take this 1 and distribute it through, through to the next one, that's just going to give me x minus the x cubed divided by 3 plus x to the 5th divided by 5 minus x to the 7th divided by 7. And maybe you want to write another term or two, but I'm just going to say that right now I'm good up to the 7th power. Hopefully I don't have to go on beyond that. Well, now I'm going to take the x and do the same thing, multiply it by every term over here. So if I do that, I have a positive x squared. I'd have a negative x to the 4th divided by 3. I'd have a positive x to the 6th divided by 5. I'd have a negative x to the 8th divided by 7. Okay, I'm not going to write anymore. Then I'm going to take this next term and multiply it through because now that's going to give me an x cubed again. So when I take this term and I say, alright, well, I'm going to multiply it through, I have x cubed divided by 2. The next term will be minus, it's going to give me x to the 5th divided by 6. The next one is going to give me a positive x to the 7th divided by 10. And I'm not going to do the next one because that one's going to bring me all the way to the power of 9. And if I only need my first 4 terms, I'm really hoping I don't have to go to the power of 9. Take your next term, multiply it through, and I'm running out of room, so I'm going to go down below and say, all right, if I multiply that through, that's a positive x to the 4th divided by 6. Multiply it to the next one, it'll give me a negative x cubed, x to the 6th, divided by 18. The next one is going to give me x to the 8th, and I guess I've done 8, so I'm going to keep it consistent through 8. X to the 8th divided by 30. But I don't have to do any more than that. Now take my next term, multiply it. I have a positive x to the 5th divided by 24. Maybe do one more, so it's minus x to the 7th divided by 72. And obviously there's more terms here. Why I did more than necessary is because sometimes terms do simplify each other out. So if I have to write my first 4, I'm going to work over here. I have this x to the power of 1, and that's the only one. So that's x. That's going to be my first term. Good, I've used that one. Maybe cross it off. It just makes it look like a bigger x. I don't know. But I've used it. Now go to your next power. And so your next power is obviously whatever you have squared. Well, I have x squared, and I only have one of them, so I'm going to add x squared. When you go to the next one, you want anything to the power of 3. So anything to the power of 3, I have a negative x cubed divided by 3, and a positive x cubed divided by 2. From there on out, everything's going to be bigger than that. So when I put those two things together, a negative 1/3 and a positive 1/2, that's going to give me a positive 1/6. So it's x cubed divided by 6. Then when I look, my next one will be to the power of 4. So my anything to the power of 4, I know I have a negative 1/3, and as I look through here, plus 1/6. So a negative 1/3 plus 1/6 is going to give me a negative 1/6. But there are my first 4 non-zero terms. And so that's my answer. Obviously, yeah, I wrote a lot more than I had to, but you do have to be careful because sometimes like the x squared might simplify out. So you can't always assume like I only have to the power of 1, 2, 3, and 4, because if all the squareds simplify out, you have to go to the power of 5. And that definitely can happen. So this is what this question is asking for when it says find your first 4 non-zero terms of this Maclaurin series. They do put series in there here, but they never told you to write a power series. Basically, they're saying like if this were a series and you maybe start at 0 and plug in your 0, you'd get x. Your next one would be x squared, then your x cubed divided by 6, etc. All right. Another long one here, I guess, is this. Find the first 3 non-zero terms of our Maclaurin series. If we have f of x equals tangent of x, this is one where I don't know the pattern for it. I do know the pattern, I'm meaning polynomial when I say that. I know my polynomial for e to the x. I know my polynomial for cosine x. I know my polynomial for sine x, and you should know your polynomial for arctangent x. But really, those are the only 4 that you should have to know. Other than that, you're going to be... Those are the only 4 that you really need, because those are pretty easy. So here's just a weird one. And whenever they say that your first 3 non-zero terms, it's kind of a bad sign almost, because it means you're going to do a lot of work that it doesn't work out real easily. So not to make this a bad problem, but there's a lot of work to it. So basically, we're just going to write out our polynomial. Again, it's Maclaurin, so that means that we're centered at 0. And as I go through, I just want to figure out wherever my coefficients are not 0, because I know that term works. Well, as I calculate this one, tangent of 0, that's 0. That's not a good start, because I have to find 3 of these now that work. When I take the first derivative, the derivative of tangent is secant squared x. When you plug in a 0, secant 0, if you don't know secant of 0, take the reciprocal of secant, which is cosine. Cosine of 0 is 1, excuse me. Now go back to secant. Well, what's the reciprocal of 1? 1. So that's a good thing, because I have a value there. That term is going to count. Yikes. Second derivative, I have to use the power rule because it's secant of x squared. So that's going to give me 2 secant x to the power of 1. The derivative of secant, using our chain rule, is secant x tangent x. Well, when you plug a 0 into this actually ends up being quite bad because it's all multiplication, and whenever you have tangent 0 is 0. So that's 0 times anything is going to give us 0. Secant of 0, remember, is 1, so we actually really like having secant. As I move on now to take my third derivative, don't keep it so separated. Put all the terms that you can together. So basically we can say, alright, we know that this is secant squared times tangent. So I don't know if it's good to erase partway through a problem. Say, I'm changing it so it looks like this. But then you have to use your product rule. So the derivative of our first term would give us 4 secant x to the power of 1. The derivative of secant is secant times tangent. And then you have to multiply it by the other term, so multiply it by tangent gives us tangent squared. So I hope that one makes sense to you for your first term. Then I have to add to it. The derivative of tangent is secant squared. Multiply it by this first stuff, so I have a 2 times secant squared will make this secant to the 4th. And that's actually really nice because we don't want any tangent as part of our term, because we know tangent of 0 is 0, so that term is basically gone. But secant of 0 is 1. So this is really nice. This will end up giving us, when we plug in a 0, we get 2 for our answer. So again, this term here is bad because it doesn't do us much good. Alright, well, we need to have 3 terms, so I have to take another derivative. Again, I have to use the product rule here. And when I take, so I'm going to start with secant squared, the derivative, power rule first, 8 secant x, the derivative is secant squared, so that will make it to the 3rd, times my second term, tangent squared x. I think that's right. Plus, actually I better check that. Should that be squared, or is that, I think that might just, it might be squared. I better redo that one. Oh, dang it. Someone just stopped in and bothered me, so I lost my train of thought. I have to put the blame on someone else. It wouldn't be me. Alright, power rule will give us 8 secant x. The derivative of secant is secant tangent times tangent would make, or times the second part, tangent squared, would make it tangent cubed. So I did have something wrong there. Plus, we're still using power rule with this thing. The derivative of tangent squared is 2 tangent x, that's the power of 1. The derivative of tangent is secant squared x, times the first thing that we have, so it was 4, that will make that an 8. Secant squared, that's going to make this a 4. That's pretty awesome. I still have the second part to it. The derivative of this thing would give us 8 secant cubed x. The derivative of secant is secant. That will make it to the 4th times tangent. Oh, this is fun. So I have 3 terms, but all 3 terms include a tangent. Therefore, this derivative, when I plug in a 0, I'm going to get 0. Ugh. Ugly. The next one will work. We get to take the 5th derivative. To start, product rule. That gives us 16 secant x to the power of 1. Derivative of secant is secant times tangent. Multiply it by the second term, that gives us tangent to the 4th. That term is ugly bad. Ugh. Plus, the derivative of this is going to give us 3 tangent squared. I don't really care about the rest because I know it's all multiplied, but I have a tangent in here. So I'm just going to say yuck and blah blah blah. I have more stuff in there. But right now this is alternating, so I'm really banking here that I'm going to get a term that does not have a tangent. And if I don't, I have to go back and fix all this. I've also done this problem, so I do know that I'm going to get one. But here, as long as I'm multiplying by tangent, I'm not even going to put it in because I know it's not going to be good. All right, let's go on to this middle portion. So now I'm going to take this part, and if I do the product rule here, okay, I have an 8. Derivative of tangent is secant squared times the second portion of this, secant to the 4th. That will just make that secant to the 6th. Yes, I know that's by itself, but you can't stop here because there might be more terms that go with it. So I do have to add to it. The derivative of secant in this situation is going to give me 4 secant cubed x. The derivative of secant is secant tangent. Yuck, I'm going to stop because I wrote a tangent. Plus, I'm going to use the product rule, the product rule with this one. So when I start, I'm actually going to take tangent first because that one works really nice. So the derivative of 8 tangent will give us 8 secant squared x times secant to the 4th will give me secant to the 6th, which is good. Plus, when I take the derivative of secant, I know I get secant tangent, so I'm going to say, ugh, that one is ugly. So basically, I know this is pretty cheap. This is not going to include anything. That's not going to include. That has a tangent. That had a tangent. But when I plug a 0 into these two terms, I would get 8 and 8. I get a coefficient of 16. That is a whole heck of a lot of product rule and derivatives. That is really, really annoying. You won't have too many that are this bad, but yikes, not fun. So our polynomial, because it just says write the first 3 terms, maybe you don't even have to write polynomial. Your first 3 terms here, you have a coefficient of 1, so it's just x, it's to the power of 1 divided by 1 factorial, we're good to go. Plus, here I have a 2, so it's 2x cubed divided by 3 factorial. Last one, it's a positive 16. That was going along with my 5th derivative, so it's x to the power of 5 divided by 5 factorial. All of that is just to get those ridiculous coefficients of 2 and 16. Whew, that's a lot of work. You should probably simplify this so it does look like x plus, ooh, if I did simplify it, it would be x cubed divided by 3. Plus, this one would end up being 2x to the 5th divided by 15. So this is why tangent's just ugly. I don't have it memorized. Maybe just remember if you see tangent, your coefficients are 1, 2, and 16, and hope that I don't put that on a test. Alright, if we move on, last thing that we have here, we want to use a power series to approximate an integral. And this is something that we cannot integrate. Because if we try and we say, well, let's let our u value equal x squared, the derivative of u equals 2x differential of x. I can't put in a 2x. I could put in a 2, but not a 2x. So I have to use a power series to approximate this thing. And basically what you want to do is rewrite this thing as a polynomial. I probably shouldn't have written this, I'm sorry. So if I want to write e to the x squared as a polynomial, I'm going to start off with a very simple series of e to the x. Maybe I shouldn't say series even. Very simple polynomial. I know e to the x is 1 plus x squared divided by 2 factorial, which is 2. X cubed divided by 3 factorial is 6. X to the 4th divided by 4 factorial is 24. And I don't know how many terms I'm going to need, but I could very easily create more if I needed to. So I have x to the 5th over 120 plus x to the 6 factorial is 720. The next one I know I'd be good because that x to the 7th is 5,000, or 7 factorial is 5,040. We do have to have an error less than 1/100th. Well, now here I'm only changing my x value. So if I want what is e to the x squared, you're only changing your x value, and instead of x, you're making it x squared. Well, I don't even have an x value, so that first term is just 1. This term is x squared. This term, in place of x, remember it's x squared, so it's x squared squared, so you have x to the 4th over 2. This term, remember it's x squared cubed, so it's going to give us x to the 6 over 6. Basically, we should know we're multiplying by 2. So x to the 8th over 24. X to the 10th over 120. Plus x to the 12th over 720. And I guess x to the 14th, if we need to go that far, over 5040. You probably don't have to be that extreme with things, but we wanted to integrate this, meaning I want to just integrate this. And if I need more terms, I can put more terms in, but I only have to be accurate to within 1/100th. So if I'm here and I have a denominator of 5040, I'm probably going to be okay. But now, all we have to do is integrate this thing. And that's pretty darn easy because you have separate terms. All power rules. So when I integrate, I get x plus x cubed divided by 3 plus x to the 5th divided by 10 plus x to the 7th divided by 42. Oh boy, this I might get out of my league here. Plus x to the 9th. Oh boy, 9 times 24. I can calculate it real quick. Would give us 216 plus x to the 11th divided by 11 times 120, 1,320. Maybe I need one more term. Probably not, but what the heck, let's just do it since we're on a roll. 13 times 720. That would give us 9,360 in the denominator. I'm probably okay, but I'm going to put dot, dot, dot. Maybe I need more terms. Probably not. I have to calculate from 0 to 1. Well, these will work out pretty nicely. Plugging in a 1, obviously you're going to get your 1 plus 1/3 plus 1/10 plus 1 over 42 plus 1 over 216. And you could go on as long as you would like here. The nice thing is when you plug in your 0, what's going to happen with every term? You're going to subtract a big fat 0 from that. So if you just have to calculate this, estimate or approximate this integral to an error of less than 1/100th, I would just start adding these together until I know that, great, I have it complete, I don't have to, or it's accurate to this amount. So I take 1 plus 1/3 plus 1/10 plus 1 divided by 42. Basically, once you get over that 1/100th, you're going to be good to go. So 1 divided by 216. And then if you try, you can plug in a whole bunch of terms, and as soon as you know it's not going to be affected, all you're going is to the nearest hundredth. So I should have 1.46. And then I'm accurate to that amount. So I think I'll probably put more like to the nearest thousandth on here. Instead of 1/100th to make you do a couple more terms, and that's not hard to do because they blow up really fast. So if you had to do an extra term or two, it's not bad. You actually even have it written down here. So 1.46 would be our answer, and that's just a whole heap of fun. So keep in mind the very simple things. You better know very easily how to write the polynomial for e to the x, for sine x, for cosine x, and for arctangent x. You want to know those polynomials. It will make your life a whole heck of a lot faster and easier. Maybe you want to pause this and write it down. I know this is an incredibly long day today, but you should know all of these things. So here would be x cubed. Even if you kept it as 3 factorial, I don't really care, but you better know these. Dot, dot, dot. Sine is an odd function, so it deals with the odd. So it's x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. We got that one. Cosine is an even function. We start with a 1 minus x squared over 2 factorial. That 1, remember, is meaning x to the power of 0 plus x to the 4th over 4 factorial minus, yikes, x to the 6th over 6 factorial plus dot, 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 dot. Arctangent is an odd function. It's a lot like sine except for it's not factorial. So it's x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7. And you can continue that. I would strongly encourage you to know those. It will make it a lot better. So remember, start with something simple. If you're only changing your x, it's very easy to do. when you're changing more than x. Maybe start crying. I don't know. And that's it. Chapter 9 in the record books. Have a great day.